So I want to talk about the final topic for the semester. I want to talk about field devices. And remember, the term field, what that means is anything outside of the PLC. So there's the virtual devices. Those are devices that exist or live in the memory of the PLC. Field devices are actually hardware that you can touch. I'm going to start talking about something we've already mentioned before early in the semester, the relay. There are relays that we use for logic, called control relays, and then there's relays, these heavy-duty relays we use for interfacing machines or devices to the PLC. So basically, as you are aware of by now, PLC relays have been replaced by solid-state devices. But back in the old days, they used relay contacts, either in series or parallel, to represent and or not logic. We can use normally open and normally closed contacts to represent not. And so I think the first day of class we talked about a relay, but just in case you want to get a physical kind of picture in your mind of what a relay looks like. So here's a simple relay, and the parts, actually we have the relay consists of two separate circuits. It consists of a coil, basically this part, and that coil is wrapped around a metal core, and the coil and the core together make up an electromagnet. Now you'll notice these wires at the bottom, they're pretty thin. These coil wires, they're thin because they have a high resistance, and what that means, high resistance means there's a low current. So the coil circuit is a low current circuit. When you provide a current to the coil, it magnetizes. And then this other part, which is, as I said, is a separate part, the armature, is basically a switch that moves up and down. And so when the coil is energized, there's a presence of a magnetic field which pulls the armature down. And when it pulls the armature down, this armature will make contact with this lower contact. Now when there's no power on the relay, then it's in the position shown in the picture. There's a spring right here that actually pulls the armature away from this bottom contact. And so if I laid this on the table with no power connected, this contact here, we refer to that as a normally closed contact. If I energize a relay and cause the armature to move down to this position on the bottom, then it connects to this contact, which is the normally open contact. So I can have a relay, I can have more than one contact, normally open and normally closed. And we talked about all of that, and you've seen the symbol for this, but just to give you a reference point, the actual mechanical device, this is what those solid-state devices inside of the PLC, what they've replaced. But that's only for the logic part of it. Relays are still used to interface large devices to the PLC, and that's kind of what we want to talk about today, at least part of what we want to talk about. Here's the symbol, the schematic symbol for a relay. And as I said, the coil circuit and the contact, you have a normally open and normally closed contact on the one I just showed you. The armature and contact circuitry is separate from the coil. There's two separate circuits. A relay is an electromechanical device that consists of an electromagnet that basically engages or disengages a switch, and the switch and the magnet are two separate circuits. And so the symbol, I can have this symbol here for the coil, so the control relay coil, and then I can have the contacts, normally open, normally closed, that relate to CR1, normally open, normally closed contacts. And so, as I said before, the relay back in the old days was actually used for and or not logic. Now it's been replaced by solid state devices, transistors, logic gates, that kind of stuff. Well, relays are still used for switching devices. As you may be aware of, you can connect some devices directly to the output of a PLC, maybe a lamp, some kind of low current device. But what if the PLC is controlling a motor, like the garage door program that you guys worked on? Or maybe even something heavier than that. What if it's controlling the elevator motor? Or something that pulls a lot of current? How would you connect that to the PLC? You can't connect it directly to the output module, but what you can do, since the coil circuit of a relay is a low current circuit, you can connect the coil circuit of a relay to a directly to a PLC, and then the actual armature can be as small or as large as you need it to be. In other words, I can use a small amount of current from the PLC to switch a large amount of current in the armature circuit because they're two separate circuits. And that's exactly what we do. So I want to talk about two other types of relays, special relays, used to switch heavy loads. And the first one is called a contactor. So basically a contactor is a relay. It has the coil. It has the part that moves the armature. But in this case, the symbol, we're showing the actual symbol here, the schematic symbol, you'll have the coil, but then you'll have these contacts. And you'll notice there's three of them. There's three contacts because the power that these things switch is called three-phase. Now, I don't want to get into the details of three-phase, but when we generate power for basically for industrial purposes, it's not exactly like the power that goes to your home. What you get at your house is you get two-phase 240 volts, and you can split that off. Two-phase 240 volts, you can split that in half, and you can get 120. So you can have a circuitry in your house. Say you plug your TV set up to, that's 120 volts AC. But maybe you have a dryer, a washer, heavy-duty dryer in your basement, and it connects to 240 volts AC. And so what's brought into your house is 240 volts, and they can split the phases down to two 120-volt phases. So you can use appliances in your house that operate off 120. So now we got choices. In industrial environments, they actually have three-phase. So they have basically three sine waves of power powering a factory. And so here, when you get into heavy-duty devices, you'll see more than one contact. You'll have three. So this L1, L2, L3 on this contactor stands for line 1, line 2, and line 3 of a three-phase power source. But basically, what you want to know here is that a contactor is just a heavy-duty relay, and it usually switches three-phase. So if you're working for, let's say, GE or Procter & Gamble in a factory type situation environment, and your PLCs can switch off and on an industrial motor, it's probably going to be three-phase, and you can't take the motor, the three-phase motor, and hook directly to the PLC. But you can take the coil of a contactor and hook that directly to the PLC, and then let these contacts, these lines, these T1, T2, T3, these poles, you can let that switch the motor. And so relays, contactors, and in a second I'll show you a motor starter. Those are all devices to interface heavy-duty motors or devices to a PLC. And basically a relay is basically two circuits, as I said. It allows a small amount of current to control a large amount of current. And so this is the contactor. After the contactor, there's something called a motor starter. So think of a contactor as a heavy-duty relay, and think of a motor starter as a contactor with an additional relay added to it for protection, overload protection. And so this is exactly as the name implies, is used to switch heavy motors. It's a special type of a contactor used to start or stop motors. And so it would look something like this on the schematic, where you have the actual contactor down at the bottom here. And as I said before, it's three-phase, so that's the reason for the L1, L2, L3, and the three contacts. So this is the actual contactor. And then here, you should recognize this as your fill-in circuit, your start-stop circuit. And then you have a main relay. You have an overload contact. And then you have each phase has its own overload contact. So a motor starter is just a contactor. And remember, a contactor is just a heavy-duty relay. So basically, this is a heavy-duty relay with another relay wired in with circuit protection to protect against overloading the circuitry. And notice again the three-phase here. So we have three sine waves we're feeding this, but that's a different topic. So relay, a basic on-off switch that's electromagnetically controlled. A contactor is a heavy-duty relay designed to switch heavy loads, and the loads are typically three-phase. And the motor starter is a special type of a contactor, which is on with its own built-in overload relay. And so typically this is what you would connect to a PLC to start or stop a motor, circuitry like what you are viewing right now. And the actual connection would look more like this. You'd have the actual motor starter here in a separate unit. So this is the actual motor starter. You have the load, which is the motor. And then down here is your PLC output module. And notice there's this one line, one small line that connects up to the motor starter. And that would be your, if we go back to our relay terminology, that would be like your contact. And that contact circuitry is a low current circuitry. So it can actually pull maybe milliamps, or worst case, maybe a few amps, but it can switch hundreds of amps. It can even switch thousands of amps if we need to do that. And so the motor starter, contactor, and relay are all special devices designed to use a small current to switch a large current, which makes them perfect interface devices to interfacing high current devices to the output of a PLC, which is a low current device. So relay, motor starter, and the contactor. And then we'll move to the other field devices, these switches. And I'm not really going to say a whole lot about the switches. You've had some experience just in your simulation software. You've seen the different kind of switches and buttons. We originally, I think the first week of class, we talked about normally open, normally close, buttons and push buttons. And there's a whole host of switches and different devices and transducers. You really could spend a whole nother 15 or 12 weeks just studying those devices. And so the main ones, though, are the ones that you have in your simulator, the ones that we talked about week 1 of the semester. Here on the PowerPoint, it says push button switches, but it might be kind of improper to think of a push button as a switch. I guess it's a type of switch, but you have push buttons and you have switches. We talked about normally open and normally closed push buttons. You can have switches that can stay in a normal open or normal closed state. There's toggle switches, knife switches, selector switches, dip switches. Toggle switches are one that you can move to one position and it'll stay there. You can move to the other position. It toggles back and forth. Knife switch is a switch that you can throw. Like in the old Frankenstein movies, they have a big lever you can throw one way to close it and throw the other way to open it. Selector switches, well, I was going to give the example of an old school TV set. But if you can think of an old school TV set where you would change the channel, it actually rotates around. So you might have 3, 4, 5, 6, 7, any number of switch positions you can adjust it to. So selector switches used to be really, really common with TV sets, and they still have some use today. And the dip switches, DIP stands for dual inline package. Those are actually tiny switches that are used to make and break contact to inputs or outputs of an integrated circuit. So if you ever had to program a garage door opener, sometimes you have to take the garage door opener apart, and there's a little, usually blue or white device with these little small switches on them. They're usually numbered. And in the garage door opener, they will use those to code the transmitter and receiver to the motor. You can actually go in and set the code. So if you ever had to do that before, if you know what I'm talking about, that's a dip switch, dual inline package. If you've never done that before, I guess these are really not that important, because typically you don't see these with PLCs unless you have some kind of special application that I'm not aware of. So the whole point is there's different types of switches and buttons out there, way more than what we talked about in this class. And if you actually get a job working with PLCs, you'll get exposed to the different switches, and there's tons of sensors. There's basically a sensor for every sense of your bodies. There's sensors that can see, there's sensors that can taste, that can feel, that can touch. There's just many types of devices out there, way more than we can possibly cover in the class like this. And again, the main ones that you use in your simulator are the ones that I would expect you to be familiar with after finishing a class like this. But just a couple of schematics, a symbol for here's some buttons that, I mean, we talked about this, normally open push button, and a normally close push button. So we talked in detail about these and how they work the first week of class. Here's a different one. Here's a make break push button. And so this one, sometimes these are momentary, sometimes they're not momentary. You can push the button and you can make contact down here and it may lock there. And then when you push the button a second time, it breaks contact and then makes contact on the side, on the top set of the pole with the top set of contacts. So sometimes these lock, sometimes this make break push button is momentary, so you actually have to hold it down to make contact with the lower. The pole makes contact with the lower set of contacts, and then when you release it, a spring will push it back here to the upper set of contacts. So you can make break position, make break contacts. And again, sometimes these are momentary, where you actually, when you release it, it goes back up to the top set of contacts. And sometimes you can press it and lock it down to the bottom. You press it again and it unlocks it and it makes contact with the top. So that's a new kind of a push button that, not new, but new to us. We haven't talked about it before. The limits, these limit switches, you've seen this symbol in your simulation software. And so a limit switch, I've actually worked with these extensively with some design stuff that I did years ago. But you can use these to find the limit of motion. And so you can have a limit switch. It looks like this. The actual switch looks like this. There's this body that's usually sealed to the environment, so it's waterproof and dustproof. And the actual switch is located in this body. And there's this arm that moves. And what you see here is a wheel. Sometimes they'll have a wheel. Sometimes you'll see these without a wheel and just have a lever here. But what happens is that you can have some kind of cam or some kind of some motion that pushes up against this lever. Inside the body, there's a switch, and that switch can be normally open and normally closed. Typically, there's 3 connection points. There'll be one, there'll be another, and then there'll be another here. And what that is you can say you're wiring something to this. You can run a wire to this. This is like the common connection right here. And then what you have here is you'll have a normally closed connection and a normally open connection here. So you can use these. These switches are usually normally open and normally closed. You have a choice. So if you want to normally close, you connect the other wire here. If you want it normally open, you connect it there. And so these are quite small. They can be really small. And so these are used to find the limit of motion often. If something moves, you can find out where the limit of motion would be with these. So these are used a lot. You have switches that, and mainly it's showing you sensors here, or switches here, but these, you really have a temperature switch, a sensor. So it's usually some kind of electronic device, but this is the schematic symbol for a temperature switch or some kind of temperature control. So your thermostat would be an example of that. So I guess here just the schematic symbol is what you would see. I don't have an actual picture of the thermostat or a temperature switch, but they do make physical temperature switches, but they're old school. Now you'll have electronic devices that sense temperature, and I guess it's kind of improper to call it the switch. It would have a switch in it, but it would be more like a sensor. Here I tried to draw, this was, oh God, this is probably back in 2004. I tried to create a pressure switch. I was thinking, well, how would I show a pressure switch? But what you have is like a little micro switch in here. And then you got this input that you can apply pressure on. And by applying pressure, it moves this pivot back. And you can either open or close the micro switch by basically applying pressure to this inlet here. Now, this isn't a real pressure switch. I just kind of made this up when I was sitting here putting the PowerPoints together 15 years ago, trying to figure out what would this pressure switch, what would it look like? And this is kind of what I came up with. In reality, these are these are piezoelectronic devices now. Most pressure switches are electronic. They don't have any moving parts. And it's not even a switch. It's more like a crystal, piezoelectronic crystal. A piezoelectronic crystal is a crystal that when you apply pressure to it, it develops a voltage. It's actually a crystal that you can squeeze, and the more pressure you put on it, the greater the voltage. And we can actually sense the voltage change, and you can relate that to a certain amount of pressure. These are the same type of crystals that's used for a crystal watch. If you have a watch that keeps time, it's based on the vibration of a crystal. These crystals, if you squeeze them, they produce a voltage. If you apply a voltage to them, they can actually vibrate, and they can vibrate so the vibration is so exact that the period of that vibration can be used to control the watch. And so the point is that this is kind of an old school mechanical switch, the way you might think of it. But as I said, nowadays pressure is measured electronically with piezoelectronic sensors. So you may be familiar with the pressure mat, or when you roll up to a stoplight on some intersections, they actually have pressure switches made into the it's not concrete, I guess it's blacktop. They can sense, or maybe going into a garage if they don't have an optical sensor, they have pressure sensors in the ground, and these are all electronic type sensors. But those are other field devices you can have, and you can connect those to a PLC. Here would be the schematic symbol for a pressure switch. You probably, if you guys work with this kind of stuff, typically electricians actually wire up. If you're in the factory, you'd have a plant electrician actually wire up the switches or sensors, and you would be the person you might program the PLC, or write the program for the PLC. And so you might have to look at schematics, which would have these kind of symbols on it. And then you would, of course, replace these switches or contacts with our examine if open, examine if closed, timers and counters and the other stuff that we talked about this semester. So this would be the schematic symbol for a pressure switch. But as I said, pressure switches are pretty much outdated. You really will have a pressure transducer, but you may come across this symbol to represent pressure. Another thing we can measure is the level of something, the level of a liquid. So you might have a big tank, and that tank might have a liquid, and when the tank is full, you might want the pump to turn off. Well, how would you figure out or find the level? Well, here's one way you could do it. And again, this is something that I might have seen in the book somewhere and tried to recreate it in my PowerPoint. I have a float, and you have the actual switch, and the switch, of course, is mounted somewhere, and the float could hang down into the tank, and when the level reached a certain position, the float would raise up and would, depending on if I have a normally open or normally closed switch, it would either open or close the switch. Again, this is a mechanical construct. This is kind of something I thought up. I'm sure nowadays this is done, again, electronically. Most of the things that used to be done mechanically years ago are done electronically nowadays. Number one, things are smaller if they're electrical. They pull, they usually last longer because there's no moving parts. So your level sensor, you can have an electronic level sensor. You don't have to have a mechanical level sensor. Now, your final exam, the one that you're going to do, is kind of based on there's a level switch. You can kind of, when you read the final exam practice problem, exam 4, is based on kind of the tank thing that I've just described to you, where there's a fluid and a level sensor in there. So you can think of this when you read, when I make it active and you actually read the final exam problem statement, kind of think of this level switch as being in the tank, and it'll make a little bit more sense to you. Here's the schematic symbol for the level sensor. So you got the one for the temperature sensor and then the level sensor. And these are still used. I mean, the actual mechanical switches have been replaced by electronic switches or sensors, but you'll still see these schematic symbols I showed you, the one for the temperature sensor or switch, and then this one, the pressure, and then the level switch. They still use these schematic symbols to represent whether you're sensing pressure, temperature, level or what have you. And so the other thing is to distinguish. I've been using, sometimes I'll use a sensor and switch as if they're one and the same, but they're actually two different devices. So a sensor, and it says here in this PowerPoint, transducers and sensors, really they're just one thing. A transducer and a sensor is the same thing. I should say a sensor is a type of transducer. So a transducer is any device that converts energy from one form to another. So an example would be a motor. A motor is a transducer. You put in electricity into a motor, you get out mechanical energy. A generator is a transducer because you put in mechanical energy, you get out electricity. A speaker is a transducer because you put in electricity, you get out acoustical energy or sound. So any device that converts energy from one form to another is a transducer. A sensor is a special type of transducer that allows us to convert some physical parameter to a voltage or current. So for example, you might have a physical parameter of temperature and convert that to a voltage. Or you might have a physical parameter of pressure and convert that to a voltage or a current. So basically, it takes some physical parameter that you might want to measure, temperature, speed, level. It takes a physical parameter and converts it to something the PLC or a digital device can understand, and that would be a voltage or current. And so there are input transducers and there are output transducers. And here I refer you to a handout. So I must have another handout somewhere that I did not put up on your Canvas. So I'll try to do that. If I don't do it, it's not that big of a deal. I would say that the big thing here is just knowing what a transducer is. A transducer is a device that converts energy from one form to another. And so those are briefly some field devices that are used often with PLCs and just electrical devices in general. Anybody have any questions or comments over anything from the PowerPoint? Okay, well, the next thing I want to talk about is, now what I want to do for design practice 3, I was looking at what I did last semester and I actually made it a quiz. I went through and I made it a quiz, and I think I went through and I kind of gave them a partial description of it, and then the class finished it as a quiz, and I counted it as quiz 11. But I promise you that quiz 10 would be your last quiz, and homework 7 would be your last homework. So I'm not going to do that. I'm not going to make it a quiz, but I still would like you to complete that practice. Before you do the exam, I still would like you to complete that design practice. So what I want to do is I have a video of it that actually goes into the description of what I'm looking for and how to do it. But let me show you what it is first. Let me just display it, and then I want to talk about something, and then I'll have you watch the video to complete it. Just realize in the video that was recorded a couple semesters ago, and in the video it says that you're going to hand it in for a grade. Just ignore that part of it. Just go through the video to see exactly how you're to put it together. But let me show you the problem, and then we'll talk about it. So for this practice problem, design practice 3, you got to understand or know what a LED is. So LEDs, I'm sure you're familiar with LEDs. An LED stands for light emitting diode. Basically it's a solid state light source. Before LEDs, all light sources were either incandescent or fluorescent. If it's incandescent, that means you have a filament that you're actually sending an electrical current through, and when you send the current through it, it heats up. When things heat up, well, some people think the hottest something can get is red hot, but actually the hottest something can get is white hot. And when it's white hot, it puts off all kind of frequencies of color. It makes white light. And the old incandescent bulbs, I'm sure you're familiar with those. You also know, if you're familiar with those, that they put out a lot of heat. So they're very inefficient light sources. The other kind of light source is a fluorescent light. Now, in a fluorescent light, they don't have filaments. There's basically an evacuated tube. It's not really evacuated, there's a gas. And when you excite the gas with a very high voltage, way more than the 110 volts you have it plugged into, it actually excites electrons in the gas, and they give off light. And so you need a high voltage for that. So you have these other circuits that you hook to your fluorescent light called a ballast. And what that does is increase the voltage enough to excite the gas so that it gives off light. So that's a much more efficient source of light. And for a long time, other than fire, those were the only ways we could produce light. Well, when I say they, when the diode was discovered, or I should say not discovered, but invented, a diode is basically an electrical device designed to allow current to flow one way and not the other. So think of it as a one-way valve for electricity. You use it for what we call current steering. Well, it turns out a side product of the diode is it gives off light. All diodes give off light. And so what scientists did, I'm talking back in probably late 50s, early 60s, what they did is they tweaked the diode, certain diodes, and they call them LEDs, light emitting diodes. All diodes give off light, but an LED is just a specially designed diode. They actually fix a lens around it, and what we focus on, or what we kind of amplify, is the light emitting part of the diode. And so an LED is a light emitting diode. Now the nice thing about it is it doesn't work, it doesn't have a filament, so it's not that you're heating up something. And there's no gas like a fluorescent light that you're exciting. I mean, it's actually electrons. As they fall from one state to another, they give off energy. Sometimes energy is given off in the form of light, but sometimes energy is given off in the form of heat, but in some cases, energy is actually given off in the form of light. In the case of an LED, as those electrons are excited by electrical current, they fall from one orbit to another in the atom, and they give off light. Now, they've actually been around, LEDs have been around for a really, really long time, but the problem has been is there's only a few colors that you can get. You can get a red LED, you can get green LEDs, and pretty much red and green were the only colors. That has something to do with the physics of the way it's produced, the light is produced. You can only produce, and you got to equate color of light with frequencies. So the LED can only give off certain frequencies of light, and the frequency color-wise would have been red or green. It wasn't until the 90s, I believe it was the 90s, that actually, there's an Ohio story for you, because there was a Dayton, Ohio. There's a young physicist, a female physicist, who, before she solved the problem of producing white light with LEDs, before she found what she found, or solved the problem, only red and green light could be produced, and so LEDs were typically used for maybe an on indicator on the circuit or an off indicator on the circuit. When the problem was solved, when they were able to produce red, any color light, white light from LEDs, then you saw LEDs took off, and that happened mainly around the late part of the 90s or early 2000s. And so now LEDs, they're used everywhere. They don't work by heating a filament up, so they're highly efficient, way more efficient than an incandescent, and many more times efficient than a fluorescent. They don't have a filament to burn out, so they last 50, 60, 70, even 100 times longer than a typical fluorescent light. And so these lights are used also from a PLC point of view. They can use also as to display information, basically to display letters of the alphabet or numbers, the digits 0 through 9. And so what you see on your screen right now is you see basically a 7-segment display. And the 7-segment display is a special kind of basically LEDs, or not just one LED, it's a group of 7 LEDs together. And so each LED is labeled with a letter of the alphabet. So this is a LED, this is a LED. There's 7 LEDs together, and they make up a figure 8. And what you have over here this is an actual integrated circuit, an IC chip. And it takes this circuit, this BCD to 7-segment decoder, to operate this 7-segment display. Well, how does a 7-segment display work? What happens, as I said before, you can display the digits 0 through 9, and what you would do is you would put in, now you got to remember BCD, what that is. Anybody remember what BCD is? What does the B, the C, and the D stand for? Anybody remember that? You may have the 29 people that's logged in, you don't remember BCD. It's binary coded decimal. And that's a special kind of a numbering system where each digit, 0 through 9, you need 4 bits to represent it. So like, for instance, a binary 9 is in binary be a 1, 0, 0, 1. Well, if you put a 1, a 0, a 0, and a 1 on the inputs, then over here it'll light up the corresponding segments over here to give you a 9. It would light up A, B, G, F, C, and D. If you put in, let's say a binary 2, so a binary 2 would be, I would need a 0 and a 1, but in BCD, you can't just have 2 bits. Every number has to be represented with 4 bits. So I would add these leading zeros, and then what it would display over here is a 2 by lighting up segment A, B, G, E, and D. And so basically I can get any digit 0 through 9 by lighting up the correct LEDs, and the way I light up the correct LED is by putting in the correct BCD number over here. And so this BCD to 7-segment decoder is the way you would drive it. So what you're going to do here for this last and final program design practice is, well, here you can read the problem statement. They say design a truth table for a 7-segment, a BCD to 7-segment display decoder, and they tell you to refer to the figure I just described, that demonstrates the relationship between 4 inputs of the decoder, A, B, C, D, and E. I'm sorry, A, B, C, and D, and the 7-segment display. So basically what you put on the input, and these are all outputs. Okay, so your truth table is gonna show the relationship between the inputs over here and the outputs over here. So let me go to the table so you can see it, and then you'll understand it a little bit better. So here's I kind of started the table for you. And so over here you have your inputs. I'm going to put a line down here. Now normally in our truth tables we just have one output. Like we just have over here maybe X or Y. But here each LED segment is an output. And then what you're going to end up doing is you're going to write over here. Here's my decimal, 1 through 15. Okay, so I kind of labeled these rows for you. What you're going to do is you're going to write over here your BCD inputs. So if you remember from when we discussed number system, BCD goes from 0 through 9. There is no 15. There is no 14. No, there's nothing above 9. So your table actually is going to be cut off right here. And do I show that? Let's see. No, I don't show that. So I got a couple tables here. So basically you can count with 4 bits 0 through 9. So all of these rows 0 through 9 will be filled. You don't need to do anything down here. So you'll fill in A, B, C, D, and you'll count 0, 1, 2 with 4 bits. And then what you want, since you have these BCD inputs, over here are those LEDs. You remember those LEDs each they were denoted by a letter from the alphabet. So you got LED A, LED B, C, all the way through G. Well, for what would it take to make a zero, a decimal 0? When I say what will it take, which segments of the 7-segment display would I have to light up in order to display 0? If I go back to the 7-segment display, you take a look at it. Well, to make a 0, I got to light up A, I got to light up B, I got to light up C, I got to light up D, I got to light up E, I got to light up F. In other words, to make the digit 0, I got to light up everything except for G. If I lit up G, I would have an 8 and not a 0. So I got to light up everything except for G. So in the truth table, that's what you want to show. I did the first row for you. In order to make a 0, and here's the BCD for 0, you light up segment A, B, C, D, all the way up through F. I would not light up G, because if I lit up G, I would have an 8 and not a 0. And so my first row, all of these are 1s if the LED is lit, and if it's not lit, I put a 0. And so that's the relationship. You got to do that for all the rows. You do that for all the rows. You probably want to do it, I guess, to be complete for all the rows through 15. But as I said, BCD only goes from 0 through 9. So technically, you don't have to go beyond 9. You don't have to go beyond this point. So then you'll have all these outputs over here and the relationship between these outputs and what you're putting in on the input. Well, then if you go back to the problem statement, what they actually want you to do is in the next part. So read number 2 to yourself, and then we'll talk about it. So it says design the truth table that will decode the 4-bit input to light up a single segment, segment A, of a 7-segment display. Write each term of the SOP in the last column of the truth table. And then I want you to use K-map techniques to find a minimized logic circuit that will light up only the segment A. So what does that mean? Well, if you go back to the chart, you would have filled out this truth table here. But if you notice the one on the bottom, on the output, we're only looking at output A. So basically what you're going to do is, again, now remember, we don't need anything above 9. So you're not using 10, 11, 12, 13, 14, or 15. You're not using any of these. But you already have this column filled out right here, A. You'll fill it out, and you'll repeat it down here. So you repeat A down here. And what you want is you want to write a Boolean term over here for any time A is a 1. You write the Boolean term for any time A is a 1. So, for instance, like for this first one, there's a 1 there. So you'd have A, you'd have B, you'd have C, and you'd have D. And then you say, all right, these are all 0, so I got to knot that. I got to knot that. I got to knot that. And I got to knot that. And that would be the term for this row right there. And then you'll do that for all the rows where A is a 1. And then you will put that into a K-map. And what I'm looking for is the minimum logic that will light up only the segment A. Now, as I said, there's a video that I recorded. It might have been last semester or the semester before. I don't remember when, but there's a video, and it actually kind of goes back over my discussion of the 7-segment display. The reason I wanted to talk about it was because in the video, this recording system I'm using wasn't working, so I wasn't able to draw on the 7-segment display or switch to the whiteboard. So I wanted to just talk about the 7-segment display so you can kind of get a mental understanding of how it works. And then I think the problem will make more sense as you go through it. But if you go through that video, it'll explain in a little bit more detail and actually show you this chart filled out. And so what I'd like for you to do, and again, when I did it in the video, it was for credit. You'll hear me tell the class, well, hey, I'm going to give you a quiz grade for this. But for you guys, I promised that we wouldn't do any more quizzes after quiz 10, and I'm going to keep my promise. So this is not a quiz grade. But what I would recommend is I'm going to unlock the final exam between tonight and tomorrow morning. And I would recommend that you guys do this practice 3 before you even look at the final exam. Now, honestly, the final exam is more like the last practice we did. When was it? Today is Friday. That we did on, no, today is Monday. The one we did on Friday. It's more like that one. But I think this will give you some understanding too. So I would recommend that you, after class, I'll post the link to the video that kind of goes back through what I just been through. Only it shows the table filled out a little bit more. I would go through that design practice, and then after that, then I would go ahead and when I activate the final exam, I would go ahead and do the final exam. And so, as I said before, the final exam is not a multiple choice. It's actually something you download. You can work on it and then upload it to me. It's set to become active on August 9th and then to become deactivated on August 9th. But I talked to a couple students. I got people going out of town. I got people trying to finish the semester early. So I decided I'm going to make it due early, and early will be either sometime tonight or tomorrow. Exam 4 will be available to you. So once you watch the video, I think this will be clear. Now you're not going to hand anything in, so I don't have any way of knowing that you did it. But just trust me, go ahead and do it before you even look at the final exam. And then I think that'll make the final exam just a little bit easier to think about. Not that it's that difficult, but I think it'll be better if you go through this design practice. So after watching the video, if anybody has any questions, just send me a text, and I'll deal with it that way. So other than that, I don't really have any more material for Wednesday or for Friday. I don't have anything else to talk about. We've covered everything that I wanted to cover in the course. So what I'm going to do is on Wednesday, I am going to be online, but I'm not going to lecture. I'm just going to check in at 1 o'clock to see if anybody has any questions or concerns. And if nobody shows up, that's fine. If you do, I'll be here as long as you need. You can ask me questions. I won't answer any questions about the exam. I won't talk about that unless it's something that's not understood. I will try to clarify, but I won't. Other than that, I won't answer any questions about exam 4. But any other concerns you might have, I can deal with that. And if nobody shows up, that's fine. If we meet for 10 minutes, that's fine. Or if we meet for an hour, I'm fine. So if you don't have any questions or concerns, you don't even have to connect to the lecture on Wednesday because it won't be a lecture. I'll just come in, check in. If everybody's cool, we'll check out, and that's it. I will be available, though, throughout the whole week by text. You can text me. I do want to say I want to thank you guys. Some of you went on, you got your exam 2s done. It's not easy to grade this stuff, especially your labs. It's just hell going through grading everybody's work. And so I really appreciate the fact that probably maybe 10 of you got your exam 2 done. If you did your exam 2 and if you texted me a link, then your exam 2 was graded. Now, if you did exam 2 and you texted me a link and you don't have a grade on Canvas, send me another link. That means I didn't see it. But you gotta complete it. You gotta post the document to Canvas, the program, the actual not the actual program, but a screenshot of the program, and then you got to send me a link either to YouTube where you posted the video, which I prefer, or if you want to send me a recording off your cell phone. But you got to text me a link, else I won't grade it. You can't just post it to Canvas because it's just too much going on. Send me the link, I'll grade it, and usually if I'm not doing anything, I'll grade it right there on the spot. So I was saying that many of you, probably 10 people, have already gotten their exam 2 done. If you did it as of right before class, I think I graded one. So anything that was sent to me before 1 o'clock today should be graded. So if for some reason you sent it to me before 1 and it's not graded, send me a text and let me know and resend your link. The same would exam 3. If you did exam 3, I graded a bunch of those on the weekend. So some of you are looking really good. You have 2 and 3 done, and all you got to do is worry about the final exam and homework 7 if you haven't done that. But many of you, I think, have all of that stuff done. So I don't really have anything else. The only other thing is I know there was a standing issue for exam 1 that there were some questions about exam 1. Now that we're done with all this stuff, I'll go ahead and I want to look at that. There was some early on, if you don't remember, there was an issue, some confusion about a couple questions I had in exam 1. So I will address that this week, and I will get back with the people who that's going to affect to let you know if there's going to be some changes or credit added, and if so, how much and to what. So I have not forgotten about that. Now we got about 5 minutes left, so let me pause for a minute and ask, does anybody, let me get off this thing so you can see me. You've been looking at that thing all the time. Can you, okay. Is there any questions or comments from me before we sign off?
I got a couple questions.
Sure.
So my first question about the exam 2, the garage door program.
Yep.
So when we're like taking the video, I know you said to like explain it. Are we just explaining like what's going on, or are we like actually explaining the code?
Yeah, so that's a good question. So what I want you to do is, just kind of, well, people did it different ways. Sometimes some people, they just went through the program without showing it. They went through the program and explained line by line what each instruction, what each rung does. And then they would show it and then kind of pan over to it. Some people went through and explained as it actually was running. There's a speed control on that. I'm sure some of you discovered that there's a speed control. You can make the program run faster or slower. Now, because we're dealing with that 10-second thing, was it 10 seconds? The 5 flashes.
Yeah.
You know, you can speed it up to show that. But at some point, you want to go through line by line and explain what each rung or what each instruction is doing. You can do it at the beginning or while it's running. The other thing, though, since you brought it up, make sure whatever feature you're adding, some people actually added another feature, and some people, how do I say it? They use a different instruction to implement a feature that was already there. So, for example, you had the flash of light 5 times. You can do that with a timer, right? You can do it with a counter and a timer together. There's different ways you can do that. Some people use other instructions to make that happen. That's okay too. That's not a new feature, but it's a new instruction used to implement a feature that was already required. So that's fine. But the point is, make sure you explain and show what that new instruction is and talk about the new feature. Some people just say, well, this is what you got to explain it. So yeah, does that answer your question?
Yeah, it did.
Okay.
And then I also had an individual question about my homework 6.
Okay, just hang on and let me see. I still got 27 people. So
okay.
Who is that talking right now?
Will, Kenny.
Will. Okay, Will. I guess I didn't know that yet. All right. I'm learning about this system still. You guys, I like face-to-face, so all this video stuff, but I've gotten used to it. But so hang on a second, Will. Anybody else have any questions over the PowerPoint, anything else, programs, any other questions before I go to something else? Any other questions? Okay, well, if you do, I'll tell you what, it's almost 2 o'clock. I'm going to stick around. So if you do, just hang on and I can either take it over video or you can send me a text. But guys, that's all I have. So as I said, we won't lecture on Wednesday. I'll just check in with you to see if there's anything that you need from me, something that I can explain, whatever. Friday, I probably won't even connect at all. I don't think we need to do that. And if you need to contact me between then, you can do it by text. And I want to say, too, before you're signing off now, but I really, really, really enjoyed the class. I think you guys asked good questions. You were perfect class. I mean, I wish I could have met some of you face-to-face, but I really did enjoy it. This camera thing is hard for me because I'm a people person. I like to do the face-to-face, but you guys made it a lot more comfortable for me, so I really appreciate it. And I hope you got something out of the course. So other than that, we'll see you around, and guys, have a great semester, and I wish you success in all your other classes. Now, Will, it's not private or personal, is it?
No.
Okay, all right. So you had a question about homework 6?
Yeah, it was just I got the organize or explain the truth table of the the Morgan's Law wrong, and you just like said to like talk to you about it.
I had the same comment on my homework as well.
I think what it was, let me go to that. And guys, thank you. Thank you guys for the nice comments. Some people were texting me. Let me see here, homework 6. So I think everybody got the, I think, and I don't know, I've had to look at your individual work, but what you want is, some people just, they didn't break it down enough for me. You know what I'm saying? So you really want to have something like this where you're, well, let me just get off of this and I'll go to the camera. So if you, I don't know which one. We can use, let's use this. Guess you can see the black. We don't need to record this. Let me